Well, thank you very much for this great conference and the invitation to talk here. It's a spectacular place, as everyone else has said. I took a bit of wine over lunch by mistake. I think Ellie was saying I would fall asleep and didn't realise I was the speaker.
Was this a mistake?
You'll see. Okay, so I'm going to try and do two sections to the talk. So part one is some work from a couple of years ago with my student Reza Dubry, who unfortunately has left physics now. And I'm going to be talking about super conformal blocks. In a slightly generalized setting, in an SUN,n/2n theory. So obviously that contains a few special cases, but the point is there's a universal structure of all of these cases. So it's interesting to look at the general case. And then part two is some recent work with Francesco Aprile and James Drummond, and a student of James's who sort of has a mirror symmetric name to me. So he's called Heineck Core. I'm Core H and he's H. Okay, and this is very closely related to Agnese's talk and the work that Fernando and Agnese have also done. So this is on order monogram to 4 corrections at large lambda.
Let me try to
to the correlation function, to the O2, 20 prime correlation function. Okay, and it's not completely unrelated, so the superblocks here help me to disentangle the free theory part in this discussion. Okay, so let me start with the superblocks. So we're looking at SUM,n/2n. So first of all, Y. There are clearly a few special cases. So n equals 4 super Young Mills corresponds to the case m equals n equals 2. So that's the group SU 2.2/4. That's the conformal group. But we also have n equals 2 superconformal field theories fit into, they have this symmetry group, that would be n equals 2, n equals 1. And, we could call it n equals 0, or this is all 4 dimensions. So 4-dimensional conformal field theory is conformal group SU 2.2. So that would be the case n equals 2, n equals 0.
how important it will be for you that you're in 4 dimensions?
Crucial throughout, yeah. It's very, very much 4-dimensional. Well, actually, you can argue about 2 dimensions. So there's a special case SU1,1/2, which at least is sort of part of the, or in SU1,1, I was just discussing with Carl actually. Like the Carl with the Roman, and then exclusive Young Mills, and part of the symmetry group. I think the blocks there, obviously you have the reverse Soror symmetry, so it's a much bigger symmetry group. But so I'm going to talk about the kind of the Mobius blocks.
Sorry, can you do 6 dimensions?
So 6 dimensions is a completely different story, where you have to start with some supergroup. But in a similar story, I forget the exact numbers that go here, but some, OSPM/n type of thing. So you can try and do that, but it's much more complicated, unfortunately. So we did make a start on very simple cases, but it's nothing like as easily generalizable as this case. Now,
you may apply this to some defect or configuration where the dimension is
Well, I don't know, maybe.
Every time the SU1,
Well, because, as I'm going to say in a minute, at the moment I'm only discussing certain 4-point functions of certain representations of this one. So scalars here and half BPS ones here. So obviously it depends exactly what you're discussing. Now it'd be interesting to see how that actually generalizes the structure I see here, but so far it's just for these special cases. So it also, by the way, includes internal purely group theory, purely finite representations of SU2n. So this SU2n is kind of SU0, 0 slash 2n in some sense. So that's the case m equals 0 and n arbitrary. So you can use anything we know about finite representations. You know, we have Littlewood Richardson and things, so you can actually try and use that sort of technology. Now, what I'm going to be looking at a bit is a kind of generalized conformal group, which is SUn, n. Okay, for arbitrary n. I'm just talking about conformal blocks, so the fact that we don't necessarily have theories with this symmetry is, you know, it's purely group theory in some sense, what I'm doing. Okay, and the key point is that there's a universal structure. Of the blocks in all of these. Well, as we'll see in a minute, something is independent of n and n. And the main motivation was to really write down the superconformal blocks in any super mills, if you like, in a sort of just write them down, so that there's some old work by Dolan and Osborne, which I believe you can decode it and obtain all of these things, but it's pretty, well, for me it's pretty tricky to do. So we wanted a kind of a formula that you could just read off.
Sorry, can you generalize also to non-BPS operators or like to quarter BPS?
So that was related to the question earlier. So, well, the answer is I haven't, no, but it would be very interesting to do so. So the question is, what aspects of the universal structure I discuss here remain? I think there should be a universal structure that remains. So, you know, well, you'll see in a bit, but basically the objects I have no indices, so it's 4 objects, it's like scalars. So it's just like scalars versus spin. So it's kind of the same problem. But now, because of this universal structure, I can try and use, for example, I can try and use some knowledge about SU2n, certain representations in SU2n to tell me about the story of conformal blocks in SU. Well, in either SU2, or
the representation inside that SU2, threshold, for instance, is important for what you are going to say. The representation of the operator
of the external thing. Yeah.
No matter if they belong, because of course also long operator or call BPS are inside that group, but then transforming a different representation. So you are saying that it's very important that the representation is the one that you are going to.
Well, to begin with, it is, yes. Everything I'm going to say here is for scalars. Yeah. Now,
Scalars,
I mean.
Sorry. I understand.
I'll tell you what I mean right now. Well, not quite right now. So first of all, let's talk about the space. So far I've just talked about symmetry group, but I'm talking about a particular space that we're living on. So we have fields in a particular space. So let's do 4-dimensional conformal field theory. Then we know the space is Minkowski space. And I can view this as a coset of SU2, and I divide everything except translation. So this is SL2 and SL2, the Lorentz group. times dilatations times special. Okay, now it tends to be easier to complexify everything. It doesn't really change much of the story. So this is the set of 4x4 matrices. So this is SL4. I complexify the group, it's just SL4, divided by the set of matrices of this form. It's a 4x4 matrix with zeros in the upper right, 2x2. These are all 2x2 blocks. This is 4x4. Okay, so this is a well-known close-up space version of Minkowski space. You can actually see from here, if people are familiar with viewing this as a Grassmannian of two planes in 4 dimensions. This is the twisted description where I have two twisters and draw a line through them. You can just view that as sort of like the upper half of this structure here. The Grassmannian of 2 planes in 4 dimensions is a 2x4 matrix up to an SL2 transformation. So this is the SL2 transformation. Okay, so that's Minkowski space. Now, it's useful to draw this as a Dinking diagram. A Dinking diagram looks like that. So this is the Dinking diagram for SL4, and I put a cross through the central node. These are called flag spaces if you're familiar with this story. The way I like to see this Dinking diagram, you can sort of draw it on here. So you've got a diagonal, and then the next to diagonal term, that is, I've got some non-zero here, then I've got 0, and then I've got a non-zero. So that the fact that I have a 0 here, but these roots correspond with each point, roughly speaking. I cross through the central node, and corresponds to having a 0 here. You don't like my... it's not very clear? Okay, I mean, maybe I can make
Do
a
we need
bit.
this picture for what follows?
Do it as 4x4.
Sorry?
If you can do it as 4x4, it could be clear.
Okay.
I understand what next to diagonal is. I just don't understand it.
So here. So this is the diagonal.
Yeah. And the next,
And the next to the diagonal is here.
Yes.
Okay, so the fact that I have 0 here is related to the fact that I crossed through this node here.
Okay.
And then the 0 sort of propagate upwards. So you can have more general flag metaphors. You can have an SL any group of crosses wherever you want, and they have kind of zeros in you know, you have a 0 here and it sort of propagates up.
So these lines should be like 45 degrees. I'm just telling you that. Is this like what are these crosses? Are
So
they
the
the
crosses
same
tells me that I
propagation
have
of
a
the
0 in my isotropy group, which I'm dividing out by at that point. At the simple group, but it then sort of propagates upwards in that direction. Okay, I mean, you can do this in a far more rigorous mathematical way, but for SL,
It's a draw. So.
for SL4, this is fine. So, but the point is, I cross through the central node of my Dinking diagram. So, let me next do. Instead of doing the super case, let me do this generalized SU n comma n. By the way, sorry, let me just say one more thing here. The reason this is useful is it kind of tells you at the same time you see the full SL4, but it also tells you this the group under which fields transform. So here I see an SL2. And an SL2, and this cross you should think of as like a U1 or in fact I'm complexifying, so it's C. Okay, so if I imagine I've removed that node, then I've got SL2 times SL2. The cross represents the U1. So So now I look at generalized SU m comma n, and I consider it on the same sort of space. It looks like well, it looks like this basically. Now everything's an n by n matrix. So generalized SU m comma n, I consider it as SLMC divided by the set of matrices of this form, where everything's n by n. SL2 and thank you, so SL2. And the corresponding linking diagram there has n minus 1 nodes, and then it has a cross in the middle, and then it has n minus 1 nodes there. Okay, and the corresponding isotropy group is SL n times SLN times C, which you can also see from here, right? It's just SLN times SLN, and the C is because I have a single trace, but that just relates the trace of there to the trace of there. So there's a leftover.
It's typically called C star, not C.
Okay, you can trace this stuff. You don't want to zero, right?
Just to
Okay.
be.
Okay, so that's this generalized space that I will be wanting to consider.
So we should not interpret these things as isometries of anything, but just as some good theoretical extension of. So I am used to think of SU2,2 as the isometries of something, but here is. So the space.
Well, I'll be wanting to write down objects like this. You know, I'm using the language of quantum field theory, but all it really is a representation theory statement. I have representations of this group, which any representation of any group I can view on a coset space as a sort of field on a coset. Even finite reps of SUN, I can put them as functions, if you like, on a coset space. So, and then you can consider 4-point functions of these guys. That's why I say it's a group theory problem. There's no quantum field theory in it, but you can still
but the space-time you will still keep it 4-dimensional.
Sorry?
The space-time you will still keep it 4-dimensional.
No, the space-time. Sorry, this is.
So it's like 4n dimensional.
Exactly, this is the space-time. So the space-time really fills in the gaps here, because I've got the full thing divided by this. So the coordinates on here are x,
Perfect.
a prime, where this is 1 to n and this is 1 to n.
Okay, so now 2n dimensional. Yes, it will be your space-time.
Well, no, m squared.
M squared.
M squared, exactly.
It's the polar.
Yes. It's just that 2 times 2 is the same.
The 2 plus 2. Okay, now the reason, the motivation for going into this direction came from analytic superspace, which has precisely this form. So let me just do the generalized superconformal group first. SUN, this is the most general sort of guy I'm talking about. So I write it down like this, I'm complexifying it, and it's useful to think of it, instead of SL2n/2n, it's more natural to think of it in this way. SLn/2n/n. Okay, this is just notation, but the reason I do it like that is because now I'm dividing by the following group. So I've got SLn/2n, so n/2n/n, and I divide by. Okay, so now I'm writing down SLn/2n/n matrix. So this is a super matrix, so it has kind of even and odd structure. And the fact that I've got n/2n/n is telling me that I've got n there, 2n there, and n there. and the same along here. It's just matrices in a vector space which has even odd structure of this form. Okay, and now I'm looking at exactly the same sort of coset space, namely this one with zeros here. And from there, like coordinates on this coset space would be written x, a prime, where a is an n/n object. And the isotropy group is SLM/n times SLM/n times C star. And then on the Dinkin diagram, the Dinkin diagram is just this one. Let me be careful. So I've got n.
These coordinates can be bosonic and fermionic.
Yeah.
Sorry, yeah, that's what I indicate by this thing. So this is E.
Yeah, so
Even odd.
It's like a chessboard.
yeah.
Okay, so the same for the space-time. So the space-time here, actually the way it's displayed here, this space-time has x. Right. This is your usual space-time coordinates that sit there in the way that I've written it. And then we have some internal coordinates, which actually look very much like space-time, they're 2 by 2. And then we have some odd analytic superspace coordinates for half the full number. But I'm generalizing this, so now alpha doesn't run from 1 to 2, it runs from 1 to n, and this runs from 1 to n. Okay, so that's the space that we're looking at now.
And you always pick 2 factors of S7?
Sorry,
In general, you could have many factors of S7.
yes, there are certainly more general spaces exist, indeed, but I'm discussing this one. Okay, so now I need to tell you what my external states are. So I want to consider 4-point functions of what I'm calling scalar representations. Charge, well, we may as well just have arbitrary charge. So the charge is this, well, again, if you've got a Dinkin diagram, you can display the representations by giving the Dinkin labels. And these are ones where I have P on this cross-through node, so that's why it's called a charge, and zeros everywhere else. Did I write down a super Dinkin diagram? I didn't write it down anyway. But for this guy, there's a super Dinkin diagram. Well, I've written it down now. So this is the super Dinkin diagram. It has n-1 nodes there. Then it has this guy, which is called an odd node. Right, and again, you can see it in the same way that I did before. If you can picture it without me having to write it out again. The off-diagonal. I have the guys here, and then I have an odd guy here. That's slightly odd node. And then I go down, then I've got a 0 over here. This is still an even 0, that's the cross-through one. And then I get down to here, I've got another odd one here. So I should say, I mean, with the superspaces, there isn't a unique super Dinkin diagram for this. This is really the same as the space SL with 2m/2n. But I wrote it deliberately like this, and then this sort of tells you what the natural Dinkin diagram should be corresponding to. So there's another Dinkin diagram. I 2n minus 1 nodes, 1 odd node, and then 2n minus 1 nodes.
And the reason it is a scalar is because it doesn't have components on the axis.
So the reason, so now I'm talking about the representation on this space, and it's a scalar just because I've got the zeros here. So the other nice thing about the linking diagrams is I can write a representation of the big group, SL4, in exactly the usual way, writing linking nodes, but then I can read off what it looks like as a field on the coset space. So here, I can read off that the representation of this SL m/n is just the trivial one, because I've got zeros everywhere. And this is the trivial one, and then I've got some weight, some charge, if you like. P.
C-star charge.
C-star charge.
That's our conformal, that's the dimension.
Yes, in the SU2,2 case, it's the dimension.
It's in this section, the line on which
Yeah.
degree thing.
Exactly. So I'm going to consider 4 of these guys. So we write it as phi P1, phi P2, phi P3, phi P4.
So in the SU2, in the usual n equals 4 superunions, this will be like the 0p0.
Yeah, exactly, yeah. That's my next. In fact, you've done both of my next points, I think. So in space-time, let me just write it out loud for you, because there's a feature which is unusual, but it has to be the case. So in space-time, p is minus delta. Right, now you know why that's the case. Because if this was positive, it would be a finite representation of SL4. Right? And this is supposed to be a scalar, this is a scalar of weight, scalar of dimension delta, okay, which is an infinite representation of SL4. So it has a negative charge there. However, when you do the super case, it turns out that all the nodes are indeed positive, even for unitary reps of the superconformal group. So this is a scalar of dimension delta. For n equals 4 CPMLs, as you just said, this is the CPO. I'm going to call it OP. This is a function of the XAA prime. Just as this guy here is a function of, let's call it X alpha dot. N equals 4 CPMLs, I have an operator charge P, and this is exactly the 0P0. And again, you can see that from the linking diagram. Again, if I wasn't doing analytic superspace, you forget about this cross through here. And you can read off everything from the superlinking diagram. That's the 0P0 that you were talking about. That is the SU4 representation.
So to get a different representation that you made in P1P.
Good question. Okay, so different representations, of course. If I have P1P here, then I have a non-trivial representation of this SU in n equals 4 of the SU2/2. So that corresponds to a field with a superindex. So phi A prime. A single superindex corresponds to a 1 here. So if I had 1, 0, 1, let's say, it would be phi A prime with some charge related to this. If I have like 2 there, it would correspond to, I think, symmetrized indices, 2 symmetrized indices. 2, 0, 2, looks like this.
Yeah, like 1, 0, 1 is the closest to the half GPS essentially.
Yeah.
It's almost.
Right, yeah. If you like it.
It's almost half GPS.
Okay, so that's that. Let me just consider the internal what I would be doing if I was doing this for a purely where I've got internal symmetry group. Because it's all combined together. Yeah?
And you put AD capital letters, that you mean just
So my
the same A that it was here?
Yeah.
which was here, yeah, these are the same. So this is the
This means that it's not a scalar anymore, or
no, sorry, but this was in reference to a question. So I'm only like these four representations here are scalars, 0, P0.
no, yeah, but I think anyway putting one on the other implies you need to have some space-time in this.
Yeah, on a field, yeah. But I'm not considering that.
Yeah, but why?
Oh, sorry. Sorry, because this, you see, this is the big thinking diagram that gives you the representation of the big group, SL, M, M, S2M. But the point of crossing through this node is that it splits the thinking diagram into two pieces. Now, a representation as a field, well, as you know from space-time, it can have indices, alpha dot indices. And this tells you what the representation of that isotropy group is. But for space-time, it's pretty trivial. You wouldn't do this, but it's the same in space-time. Right? If I can consider a spinner, and it looks like, I think it's like that. That would be a psi alpha dot massless spinner. Right? Alpha, sorry. That one there tells me I have a fundamental representation of this SL2.
Yeah, no, but I thought the coordinates indices were the one that were more the most external ones.
The furthest to the side. Here you're putting ones on
So
what
I
look like
can
the...
put
Oh, okay.
only R symmetry indices.
Well, you can discuss which way around to put the thinking down.
Have you chosen?
Yeah, no, you have to do it the right way around. In fact, unitary representations of superconformal group always have, well, okay, it depends on your convention, but in my convention, downstairs indices, and it works like this. So this really is the A.
Okay.
You cannot get an upstairs index as a unitary. You never see an upstairs index if you're considering unitary reps of the superconformal group. They're not equivalent in superspace as they are in.
Sorry, what unitary means in your language, like only at the level of
Well,
group theory?
in n equals 4 superangles, then you only get downstairs indices for unitary reps. Okay. So, yeah, I wanted to quickly just talk about the SU2M case. We could also consider SU2M, and that looks actually very similar to the SUM, M case. So what's the difference? Well, it's just the sign of the node in the middle, really. So here, this sign really is plus P rather than minus P. So this representation well, you know what this representation is of SU2N. It corresponds to a Young tableau of length of width P and height N inside, well, obviously the maximum height you can have is 2N. So you're looking at, if you want to consider this internal case, you're looking at a product of 4 of these representations, and you're asking, conformal block asks, in the tensor product of 2 of these, what is crossing between the two sides of the 4 products. Okay, so that's what we're doing. It's quite, the setup is quite general, but in the end, I am just considering 4 fields. You can just think of, you can just think of space-time and normal conformal field theory. So I'm looking at a 4-point function: P1, P2, P3, P4, where P1 means this representation. These are via x with some charge p associated with it. Okay, and then I look at them and I...
Sorry, and they will be protected and have BS, etc. by representation theory, basically.
In the super case, yeah, these are always going to be short. Yeah. I mean, in the scale, in this case, Denmark, in the case delta equals 1,
I mean, that's together.
So these are half BPS in n equals 4.
Can I ask you a silly question, maybe, for your level of things? Like, if you compute 2-point functions and 3-point functions, do you find, again, that these things are protected? Well, 2-point functions, you just said. But if you compute 3-point functions...
Are protected?
Yeah.
But how would you see that? I mean, you know, the protection mechanism in n equals 4 is via this trick of an interrogator, right?
Yes.
He relates it to a higher point function with a Lagrangian insertion.
So here you don't have a Lagrangian.
Right, yeah, I think, I mean, you could probably...
But can't you act with Qs, for instance, like if you act with supercharges, can't you see that like an insertion would be acting with some S or Q, depending on your...
I mean, Q is just, I mean, okay, Q is a mixture here of a superindex, if you have one, like choosing a different component of this superindex. Now, in the half BPS case, you don't have a superindex, so Q is only, and that's related to the fact that it's, it's half BPS. So if some of the Qs are missing, that's the same statement as having no superindices. But also this X contains some superspace coordinates, so Q also corresponds to, like half the Q is going up in this X coordinate, and the other half can correspond to a superindex.
Now, if you have n equals 4 superconformal and n equals 4 supersymmetry, you can always say that in the tensor multiplet of the stress tensor, you have a marginal deformation, a marginal operator, which is the Lagrangian. Can you say the same here? Is it true that you will always have? Isn't it true that you will always have?
I mean, I don't really want to take these things seriously. I mean, it's for me, it's group theory. I mean, I'm just doing group theory. I don't think. I mean, of course, it's interesting to discuss if it has any physical meaning.
Right. Yeah, that was the question.
Right.
You can physically try to interpret this as some sort of theory or like.
Yeah, that's not something. That wasn't really the sort of motivation behind it. But yeah, we can certainly discuss that. So we have a prefactor which just absorbs the weights. I can write it down if we're interested. But it's the usual sort of. Well, maybe I can write it down. So D12 to the P1 is P2 over 2. G34 to the P3 plus P4 over 2. G24 divided by G14 to the half P2 minus P1. And then G14 over G13 to the power of a half P4 minus P3. That's just to give you an idea of what I mean by that. So the Gij here is the superdeterminant, or the inverse of the superdeterminant of xi minus xj.
Would it be X over Y? Or?
So this is the super x. So this x here, very good question. So in n equals 4 you've gone, this x is, well, okay, it's written a funny way around. If I swap it back to a more standard way of writing it, I've got x and then y there. And a superdeterminant is given by a determinant of this piece divided by a determinant of this piece. So this becomes y squared over x squared. That was your question?
Yeah.
Right.
So this is the analog of these yij's, which you got in n equals 4. Or?
These are, yeah.
This is X over Y, Y over X.
Yeah, I see. Right. So then you know this translation. Yeah.
so in the bosonic case, you can forget about the superdeterminant. It's just the determinant inverse of xi minus xj, which is 1 over xij squared. In the super case, there's also a fraction of the numerator. Okay, good. So now I say it has this form, conformal invariant. What's a conformal invariant in this theory? A conformal invariant is any function of z equals x1, 2, x2, 4 inverse, x4, 3, x3, 1 inverse. So this has indices A and B, if I have a couple of indices together, such that f of z is equal to f of n z inverse. Okay, in other words, it only depends on the eigenvalues. It's just a funny way of doing usual. We know that in conformal field theory, 4-point functions depend on cross ratios. This is just a funny way of saying the same thing. So in space-time, what does this translate to? It translates to exactly what we said, but these are space-time coordinates. And now I'm thinking of it as a matrix, it's a 2x2 matrix. It's invariant under this. And that corresponds to the eigenvalues are actually x1. Well, I'm calling them x1 and x2 there, what you call z and z bar. Okay, and that's actually very easy to see. You can see that x1 times x2 is of course equal to the determinant of z. Right? These are if z is equivalent to x1, x2, that's what this means, then the determinant is x1, x2. And then the other formula is similar. Right. The other formula for this. So this is what was called u in years as well. And then there was 1 minus x1, 1 minus x2 equals the determinant of 1 minus z equals d. This is for space-time only. But it generalizes to m x's. More generally, obviously we've got m x's and n y's. Okay.
Sorry, so you say that so that the number of, so I am a little lost. So the number of cross ratios, you say it is like n or something like that.
Yes, exactly.
This conformal like the sigma and tau, no? As well, the one with y's.
I am fine with that, but I thought that if you computed a 4-point correlator in any number of dimensions.
But this isn't just, this is
It's not dimensions,
this is
no.
another Lorentz.
I know.
This is another.
Yeah.
It's just some, it's
Okay,
just
so there are these m.
some mathematical generalizations.
Yeah. No, I understand. I was just trying to.
But you see, maybe the way to think of it is in n equals 4, you have two sort of internal cross ratios. Whereas if you're doing n equals 2, there's only one internal cross ratio.
But it's actually true if you take m equals 1, that is one dimension where you don't have two independent cross ratios.
Very good, yeah, like
Yes,
a two-dimensional
exactly.
case. Yeah, that is the one case you can think of in terms of space-time.
Yes.
Okay, so that's so a 4-point function is written as a function of these guys, and the useful basis is the Schur polynomials. And that is simply a trace, or a super trace if you're in the super case, over a representation of Z. So this is a rep of the smaller group, right? GLM/N. So, for example, the super trace of, if I label my box function by Young tableau, that's the fundamental representation. That just means the trace of Z. So that would be just an x1, and well, the super trace is there. So the x1 up to xn. Super traces, just as super determinants have a ratio of determinants, super traces have a sign in them. So it's the trace minus the trace. Okay, so that's one guy. The super trace, I'm just going to give you two examples to give you an idea. So this guy simply means I take two copies of my Z and symmetrize the indices and then take the trace, so I can write it like that. So if I write it out, it's a half. So there's two terms here. One where it's A and B, that gives me a half a trace of Z squared. And the other term where it's BA, in which case it's trace of Z squared.
But super trace.
Super trace, yeah, sorry. Super trace of Z squared, of course, is just x1 squared to xn squared minus y1 squared to y1 squared. Okay, but there's an explicit formula in the for all of these things.
The 1/2 is in both, no?
Yeah. And the antisymmetric guy is exactly the same with the minus sign. So in principle, you can sort of try and work them out using Young tableau. Okay, but there's explicit formulae known for these. So, by the way, someone asked about 6 dimensions. So here, this property doesn't hold anymore. So you have to try and figure out, even the basis you're expanding, and you have to try and figure out a formula for it. Okay, so for the n equals 0 case, this is this sort of generalized space-time. These are just this is just the Bible character formula. Trace over, and I'm now using this to represent a Young tableau. With columns lambda 1, sorry, with rows lambda 1, lambda 2, lambda 3, and so on. It's represented by this lambda. Okay, and it's simply given by the determinant of the little x I lambda j plus n minus j. So this I'm thinking of as a matrix from an ij matrix, I running from 1 to n and j running from 1 to n. 1 less than or equal to I, j less than or equal to n. Divided by a very similar determinant, but simpler. So it's just given by this formula.
Xi.
Sorry?
It's not clear. Xi.
Exactly. And this is essentially the random one determinant. You can rewrite it as a product of factors of the form xi minus xj. Okay, let me illustrate that in one case, just to get slightly back down to earth. So in the case of space-time, this reads, I have a trace of a guy lambda 1, another guy lambda 2, and it's equal to x1, x2 to the power of lambda 2, x1 to the power of lambda 1 minus lambda 2 plus 1 minus x2 to the same power divided by x1 minus x2. Okay, that's what that formula becomes. You can check if you've never seen this sort of thing before. If you look at this formula, it should agree with that formula.
So,
okay, now this, yeah, well I can say more, but this is essentially the twist that Nietzsche talks about. And lambda 1 minus lambda 2 is the spin. Okay, but this is what we're expanding our function in. We've got a 4-point function, we're expanding it in these things. Right, okay, so conformal blocks. How am I doing for time?
So just to, I see, so at the end of the day, you will have u to some lambda, and then you expand, it's like the characters of SU2 basically,
Right,
written in terms of sets of bar.
right, exactly.
About 5 minutes to the coffee break.
Okay, thank you. So let's try and get on to the conformal blocks. So, okay, what is a conformal block? Well, I mean, we had this very nice introduction to this by Niels, so I don't need to say too much about what it is, hopefully. So it's the contribution to the 4-point function of some operator. Operator here means representation of my group. So my operator now, as we've sort of been discussing a little bit already, instead of being zeros everywhere, it's going to have a gamma here, or at least it's related to something called gamma. And this is all very general, of course. And then it's got my lambdas, which give me my SL m/n rep. And in the 4-point function, this representation is the same as that representation. Actually, the way it's written is, it's flipped because the Dinkin diagram is back to front end.
So before you go ahead, so here you have a conformal field theory with this extended group, etc. Where is the stress tensor?
Where is the stress tensor? Well, it's in different places. I mean, if I'm looking at n equals 4 super-Young males, you know the stress tensor is the case with the 2 there, and it's in that multiple somewhere.
Right. Yeah.
And for n equals 2, super-Young males, however, it's actually a guy with indices. It has super indices. So, I mean, it's not a universal.
I see.
It's not sitting in the same place.
I see.
In the physical cases. And then, for space-time, I know it has alpha dot beta indices.
Right.
So it has a 2, it's 2, and I don't know what the node in the middle is, but something like -5 or something like
Sorry,
this.
can you look at these lambdas that you have? So you should have some lambda 2, which is a specific. So can you fix the representation already by looking at what you had in the box upstairs? You write.
Yeah, so this is lambda, and from the lambda I can read off the Dinkin labels here.
So
In the space in the bosonic case, that's very straightforward. The Dinkin labels are essentially the
yeah, you wrote like that lambda 2 is the twist, lambda 1 minus lambda 2 is the spin, and this specify completely
Yes.
the operator, so from that you can read off where is the
Exactly. Yeah.
case that the lambdas were the same on either side just has to do with the fact that you're doing this for these special scalars.
Absolutely.
It's very confusing because in empathy to fix the stress and extension, if you write with nice components, it starts with a nice scalar, and now you need to have a super field.
Yeah, no, I agree.
Why this is like this?
Yeah,
Because the arm charges is part of.
the hypermultiplets though. Hypermultiplets are scalars for me. Right? They don't have indices. So, you know.
But the Kailan, the one that Mario was talking, how many?
He has many indices indeed, yeah. Yeah, so,
It's very good. Because there is a slight generalization of your story when instead of doing n comma n slash 2n, you have n comma n slash some other number.
that's not even.
That is not even.
Mm-hmm. Yeah, I can't fit it into quite this story because I have the same groups. I have the same two groups. And I put it right in the left. But certainly you can discuss more general cases, yeah.
I mean, we're just saying that if you change concept, keep it without indices.
Mm-hmm. Oh yeah, no, of course. You can consider fields on various different superspaces. You know, so quarter BPS, in any what's called quarter BPS, multiplets are most naturally perhaps thought on not on this space, but on a different coset where I cross through some of the other nodes. But you can also consider them on this space, they just happen to have super indices. Okay, so let me try and get to the conformal blocks now. So the operators that are being transferred, I'm labeling with gamma and lambda. So that's my operator and its function of x, a. Oh, where's my bell? Let me write that down. Okay. I've got a key point here, so let me try and write that down. So the key point here is that P1, P2, P3, P4 is equal to this prefactor that I wrote down times the sum over gamma and lambda. But actually it's the sum over operators, and then more than one operator with the same representation. So I should probably have another index to indicate that. Times G13, G24 divided by G12, G34 to the power gamma times something I'm calling F alpha beta gamma lambda. Z. This, if you like, is the conformal block for me. And F alpha beta gamma. F alpha beta gamma lambda. Sorry, alpha beta, I should say what these are. So gamma is this gamma. And alpha and beta, if they're equal charges, alpha and beta is just half gamma. If they're different charges, then these change a little bit. But I don't want to write the precise formula
So
down.
this is for identical.
No, this is for any charges. It's just that alpha and beta depend on the differences of the charges. And I'm not writing down the formula, but
As usual, yeah.
I mean, it's in the paper. So the conformal blocks is what we want to write down is equal to the sum over mu, which contains lambda. So this is Young tableau, if you like, it contains the initial Young tableau. And then I've got some coefficients. And then I've got the shared polynomials. Okay, so it's an expansion in shared polynomials. These are known, but the key point that I want to make here is that these are independent of my group. These coefficients. that in the space-time case, I can write it like this, I can read off these coefficients, and then I can use the same formulae in n equals 4 CPMLs. You say that can't be right, there must be more information. Well, the point is this guy is cut off. Right? In space-time, this is SL2 representation, and I can't anti-symmetrize it. I only get 2 row cases. So that's why I have to go to a higher generalized space. Okay, let me...
But it's still an infinite sum? I mean,
it's an infinite sum. I can give you... we do have specific formulae in all the cases, actually. I'm only going to give you the one for this generalized space-time, actually. But the sort of the universality property, which which sort of motivates the point of going to this generalized case is this point there.
Sorry, so alpha, beta, and gamma are indices for the external guys.
No, gamma
and
is.
Lambda.
Yeah, well, gamma is this gamma. This gamma.
So it's this external.
Internal.
This is the internal. This is the
So
thing being
lambda
transferred.
and gamma are the internal,
Yeah.
and the alpha and beta are the external.
Well, alpha and beta depend on gamma and also a little bit on the p's.
I see.
In the equal charge case, this is gamma over 2, gamma over 2, gamma. And they're the sort of things that appear in the 2F1s, right?
Yes.
Delta 1, 2.
So the dimension, like the piece enters into that harmony.
Yeah. Okay, let's okay, so these coefficients are known, they're quite nice. I'm not going to talk about the coefficients much. I'm going to instead give you a formula to sum these up. So this is given as an expansion in shared polynomials. We can sum up the expansion. Okay, so first let's look at the cases we know. So in SU2, 2, at least in this form I'm going to write, then this is written down by Dolan Osborne. And they have F, alpha, beta, gamma, lambda, and Z is equal to x1 to the lambda 1 plus 1, x2 to the lambda 2, 2f1, lambda 1 plus alpha, lambda 1 plus beta, 2 lambda 1 plus gamma, and x1, and then we have another 2f1 with x2. So the arguments here are lambda 2 plus alpha minus 1, and then sort of fairly obvious general the pattern from there.
So in your general case, the conformal blocks will also be the eigenfunctions of some Casimir, right?
Yeah, they have to be, but that's not what I use to find them. Okay, so that's the formula for SU2, 2. So what we actually do is just write down, well, first of all, notice that this is equal to the determinant of xi lambda j plus 2 minus j 2f1 lambda j plus 1 minus plus alpha. And then I won't bother with the other guys. xi. 2 by 2 determinant, right? I've got this times this minus that times that. It's a 2 by... This top row is a 2 by 2 determinant. Okay, and divided by, well, this
And you will say that the two-dimensional conformal block can also be written as a determinant.
So yeah, so now I say that all of these guys, so for SUM comma n, it's the same formula. In fact, I don't need to rewrite it, do I? So SUM comma n is given by exactly the same formula for I now runs from 1 to n, and j from 1 to n. It's just now a bigger matrix. On the bottom I have the random non-determinant, again, which I had before, the determinant of x, I, n minus j. Okay, so somewhere, well, it's gone now, but if you recall the formula for the characters, circle numbers, they essentially look like the same formula, but with the 2f1 removed. So the first, that's the first term of the expansion from the 2f1 is 1. So this is the SUM generalization.
Sorry, does this follow from your sum, like from summing explicitly the things you knew, or it is just?
No, this is essentially written down. I mean, the motivation, the original. There's a bit of a complicated story as to how we got there. Actually, there's also these Y conformal blocks. The internal conformal blocks. If you write that in this language, and you write it in this language, you find that it's actually very strange. These coefficients are exactly the same, but in a very non-trivial way. So to get these coefficients, you write down a term and then you sum over a Weyl group. And then to get the internal ones, you sum over a Weyl group in a different direction. Yes, yes. So anyway, so the way we got there, I think, is that we found a formula for the R's, a natural generalization for the R's, and then this was kind of fairly
Sure, can you share one sentence on the R's?
Well, I suppose it was a guess, essentially. So we looked at the known R's for the cases of Dom and Osborne. And then, as I said, for a while I was trying to combine them. So I knew this would be true, the same R. But then the internal ones looked very different. And then it took me a while to realise that they were precisely the same, even though you get them from a very different formula. It's kind of hard to explain without going through the details. But these R's are sums of some little r's, which are non-numerals in integers. They're rational. Sum over a Weyl group to get the internal versions of the R's. I do a similar thing, but it's a different sum, and they magically work out to be the same. So then we try to look at a generalization, SUM comma n. There is a natural generalization. If you write, in some sense, if you write the lambda rep, and then you write the mu rep, write the mu, I'm summing over lambda and mu. And essentially what you do is you sort of fill up this guy with, I forget the details, but there's some way of thinking about it. You put numbers in the gaps. It's natural if you've sort of seen the formula from before, and that gives you the, I didn't prepare that stuff, and it's a while since I did, so I don't have the details in any more precise way than that.
Sorry, are you saying this F that you wrote is just not the internal one, so this is only the...
This is everything, so this is...
Okay, so are you
Sorry.
contained...
So this doesn't say anything, this just says I can expand it in circle. But these R's are universal. and, I mean, that's maybe one way of phrasing it. I can extract the R's from this formula because of the universality. If I now rewrite this formula like that, in the SUM, case, these are precisely the same R's as for the analytic superspace case.
Yeah, but how do you get the F? The F, you write. I thought that you were, by knowing the R, you were able to write the F.
Yes.
So,
Well, we guessed the R, and then we also saw that it worked. It satisfies these non-trivial identities that I was talking about. So if I write down an R for SUM content, I can also write a similar R for the internal group SU2N, and they agree very non-trivial. I don't understand if this is something that mathematicians
for all
know.
cases.
Yes, exactly. Very non-trivial cases. But I mean, I think it's fair to say we haven't really tried that, I suppose, to be honest. I mean, it's just a natural guess.
But I'm sorry, you could just take the Dolan-Osborne result and use them to deduce the R's, is that correct?
Yes, but only, good. So, but only, because that's SU2, you only get 2 row Young
Ah. I see.
So that gives you correctly the R's in that case, when lambda and mu are only 2 rows.
But sorry, I'm a little confused what is derived and what is like. But, so today when you said that the coefficients are independent of the group Mn, that is because of the structure of the things you do, or you are assuming?
Well, I think the argument for that is simply that I can reduce both sides. I can reduce the conformal block, set xn to 0, set y to 0. Imagine I have the infinite case.
Yeah, I agree.
And then this reduces, and the whole thing reduces, and I see these guys are reduced. Okay, so we also have we also have a summed up formula for the supercase. It's not too much more complicated. It's a bigger determinant, but the main emphasis of
This is going to be done.
So the main point I wanted to make is kind of a new perspective for me, really, is that instead of taking free theory, and the first point is that the free theory is the hard one. Free theory is difficult from the point of view of superconformal blocks. The interacting theory, as Agneta was saying, has this factor, and the blocks have a factor, and they factorize into external and internal blocks. So that's, in some sense, from the point of view of superconformal blocks, the waves there are the easy bits. The free theory is the hard bit. So the sort of new perspective, the easy way to do the superconformal partial wave expansion for a free theory is basically to convert it to SU n, n, where n is large enough so that I don't miss any representation. So in the superblocks I'm going to have, depending on the charges of the operators, I get Young tableau of a certain height related to the p's. So I need to take my SUM, m group to be, m needs to be as big as p, essentially. So let's just do a stupid example. 2, 2, 2, 2. So this is like super young wells, n equals 4. It's given by 4 n squared minus 1 squared g1 2 to the 4 g3 4 to the 4. Okay, this actually is in different notation. This is the same formula that Agnese wrote down earlier. These are the kind of, this is the disconnected part like this. G1, 2, 3, 4. And then there's another piece which is G1, 2, G2, 3, G3, 4, G4, 1. Okay, and we can expand that in a superconformal, into say superconformal blocks if we want. Instead of doing that, I just view this. Everything here has a natural it's not even a generalization, it's a truncation if you like, in this case. It has a version in SU2, 2. Right? G12 is the superdeterminant of an X12 inverse. So I can convert the whole problem SU. In this case, I can do SU2, 2. I just have to, I don't even have to do anything. I just have to reinterpret what these symbols mean. Now, why is SU2, 2 enough? For this chart, 2, 2, 2, 2, 2, you only ever see Young tableau of 2 rows. Therefore, that is enough. Okay, so I write down this, I write it as a prefactor, I write it in this form, not quite that form, it was written there. I write it as a prefactor times the sum over conformal blocks, but I use these conformal blocks. And my space is this generalized space-time. And well, basically, in terms of what you need to know, this is the only formula you then really need to do the conformal blocks. Of course, you need to be able to interpret the quantum numbers, which is a pain.
So you take n equals 4 superior mills.
Yep.
I thought that had already this SU2, 2. So
This is.
slash 2, I see. Right, okay, I see.
Let me do another case because maybe this is too easy. I can do 3, 3, 3.
Sorry, can you please before go to the hard example, no?
Okay.
Like, so this one, we know that there are the 6 different representations. How do you see what you are erasing?
How do I?
So the 2, 2, 2, 2 in the block that you are about to erase.
Right.
There should be the contribution of all the 6 representations, which we know the 4-point function can be written in. Where are they in the formula there?
So, I mean, everything is there. So I have a gamma,
Yeah.
which can be 0, 1, and 2. And I have a lambda, which is any Young tableau of this form. So I have lambda 1 and lambda 2 essentially. And this is my operator. So if I do this expansion, I obtain the conformal block for an operator L gamma lambda transform.
For instance, if I want the operator transforming in the 20 prime, which index should have?
1, 0.
In 20 prime. Well, I mean, I'm not thinking, I don't have this actually, I'm thinking of supermultiplets. I have the supermultiplets.
But also the super.
So the 0, okay, sorry, I mean, maybe this is the answer. So 0, 0, 0 sits in this sector, gamma equals 2.
Okay.
And I think the 0, 2, 0 therefore sits in those sectors.
Okay, so essentially you're saying that the gamma, what you call gamma,
Yes.
is the internal
Yeah, right.
index, and the lambda is the dimension and the spin.
Yeah. Okay, and then you can do a similar thing for 3333, but there you really need to go to SU3, and so on and so forth. Anyway, so this is a kind of neat way of doing super blocks, basically. So that's the end of part one. Any more questions on that? Okay, so this was, if you like, okay, just one of the inputs for the next thing I'm going to talk about. So, so this is this order 1 over n to the 4th contribution to. Now we'll just focus on this correlator, 2, 2, 2, 2. It's given by a free theory part plus this prefactor times x1 minus y1, x1 minus y2, x2 minus y1, x2 minus y2 times f of x1, x2, lambda n. This is a fully non-perturbative statement known as partial non-renormalization, which I found a while ago.
Do you understand what is special about the free result? That always puzzles me. Imagine that you are discussing this at lambda or g n is equals 1.
Well, it's the same. I think it's the same statement as the fact that short representations are protected, so that only long representations sit here. Okay. All the short representations sit here, and we know that their 3-point functions are protected. So, in some sense, this object here, which contains all the short stuff, is protected, and that is the same as the free theory.
Sorry, free you mean that or something else?
Yeah, indeed, very good.
And then it's not so simple, right?
What's
the free result is much simpler than the representation of the short contributions. So the representation of the short.
Yeah, no, that's true. There's long stuff in there as well.
Right.
But okay. So how to put it? But there you can stick there, almost stuck in arbitrarily, if you like. So my argument, I think, is still valid.
Yeah, sure. Yeah.
But you're right. It's a bit misleading because this isn't just short stuff. This is short plus long.
Yeah.
But it's really the correction. The main point is the corrections are all long. That's the key point.
Yeah.
The corrections are all long, and therefore the G dependent sits here.
Sorry, but so the way in which you write is really that the right-hand side is only for long, non-protected.
Yeah.
So you cannot put the long free on the right-hand side. Not the right side, the second.
Well, you can. I can subtract something of this form from here and put it to there.
And
No,
are you going to do that or not?
Sorry?
Are you going to
No.
do it? Okay.
So this is a result of the 4-point function at g n is equal 0.
This is yes. Yeah. Exactly. Okay, and this is depends on lambda and n. But now we right. So this f. So consider f of x1, x2. Okay, I'm getting a bit. I want to pull out this factor. Let me just renormalize everything so I don't have this factor in. I hope you forgive me for doing this. It's terrible. I know. This is 4 over n squared. So this is the free thing. Right. So now I'm considering this function, and I want to consider it in the limit lambda goes large lambda as an expansion in 1 over n. So I have A times F supergravity plus A squared times F string loop. Okay, and then in principle we've got order A cubed, and this is all up to potential lambda to the minus quarter groups.
So, are you, I'm a little confused by the notation string loop. Are you considering string states or not?
This is the same thing that you're considering. Right? This is 1 over n to the 4th. So A here is 1 over n squared minus 1.
But you are not considering what you would call alpha prime corrections.
No, that's the thing here.
So it would be more like a looping subgraph.
Yeah. Oh, okay. So
Yeah, no, it's just, sorry, it's just a,
yeah, right.
I see. So right.
So this thing is known. This was calculated a long time ago by people like Doug and Friedman and Aristotelian and Prolog, I think, wrote it in this form. And I'm probably missing people, maybe it's Cyclone. Hopefully I'm not missing anyone here. So the question is, what is this guy? And as we were discussing earlier, in principle, you could try and do it using weapon diagrams. Instead, we're going to do a similar story to what you were discussing earlier. So, nicely, you presented a more precise version of what I'm going to write next. So I can refer to your talk for the precise details. So, let's go back to a block expansion. So forget all the superblocks and everything for a moment. Roughly speaking, the block expansion is the sum over some coefficient, which now depends on the coupling A, times, let me stick with my notation from before at least, so this is U, it's the power of, well actually it's the twist, isn't it, that goes there. Tor of A times something I'm just going to call F2, x1, x2, A. So again, this is a conformal block. As this sort of more schematic form. So these, and they depend on the spin, tau, and L. And I can do the super case as well. But I just want to actually repeat the point that you made earlier. If I now do d with the A on this, then I have a term A of 0 times log x1, x2 times delta prime 0, and then times f2 and times u to the tau. Plus a non-log. I just did that by doing dBA on this thing. If I do dBA on that, this is tau prime. Delta and tau are effectively the same. So this is delta minus that. Order A squared, I have A of 0, differentiate again, and I have a term which is log squared x1, x2, delta prime of 0 squared f tilde u to the tau plus log to the 0. This is log x1, x2. So if we have the order A piece, this is the order A piece, we know that, then we have this information, and from the leading order piece we have A of 0 as well. Therefore it looks like I can obtain the log squared U piece. However, as we heard earlier, that's a bit too fast, because there's more than one operator in the game, with the same twist and the same spin. Okay, so looks like we can bootstrap log squared U order A squared piece from log U order A piece. Actually, you can do that for the twist 4 operator, which is the sort of leading U mark. There is only one twist 4 operator. And we tried that a long, long time ago, over a decade ago, and played the same trick I'm going to play now. But there wasn't enough information there, basically. It wasn't the right answer, it turns out. Well, I'll say a bit more about that in a second. So, the problem is there's more than one operator. So in free theory, we have the sum of AI.
Sorry, by free theory you mean large and large lambda?
Yeah.
Yes, it's not right. Yeah, it's
Yes, sorry, I don't think it is. Order H is which is the free disconnected theory, of course. But, I mean, I didn't do that, but obviously this thing gives me A of 0. So it's not A of 0, it's the sum of AI's of 0. Order A log U, I can extract by doing a block expansion, I can extract the sum of delta I AI, and then order A squared log squared U, I can extract the sum of delta squared I AI. Okay, so I can't bootstrap from there to there, in fact, because of this sum. At least not directly, using just the 222 guy. So let's consider what other information we have. So because this is motivated by the recent, well, I don't know how, maybe not so recent anymore, but results of Rastelli and Zhu, who computed arbitrary charge order A correlation functions. Okay, so let's consider what other information is. So here, first point is that AI is really equal to C2 to ICL squared. Okay, let's consider all 3-point functions of the form CPP ITL and all anomalous dimensions. So this is OP, my RPBS times OITL. So this is twist, this is spin, and this is the extra label, non-quantum label. Okay, so how many are there? Well, let's look schematically. Operators of spin, L, twist, turn are of the form OP, D to the S, box, T minus P, OP. Actually, well, this is when P equals 2 to T. I should have tried to align my label. I mean, P minus 1 is effectively this I index. Okay, so what am I saying here? What I'm saying is that this assumes one no single trace slash string states and two no triple trace at this order. So the only operators, the only long operators we have of this form. And here these have actually four indices which are contracted. Okay, so we assume that so how many operators are there? There are T minus 1 operators. T minus 1 hops of twist T. So this sum here goes from 1 to T minus 1. Okay, and now the other fact is that they contribute to the following OPs. So they contribute to the OPs of OP, but only for certain values of P. So they contribute to the OPE O2, essentially everything contributes to that guy, O3, O4, but only up to OT. So what do we find? So there are T minus 1 squared plus T minus 1 equals T minus 1 pieces of data we need. Okay, so what's this T minus 1 squared? This is C, P, P, T, L, I. So here P is running from, so here P goes from 2 to T. P runs from 2 to T, and I runs from 1 to T minus 1. So it's T minus 1 squared, different pieces of information. And we also want the anomalous dimension, which I'm calling eta, depending on T, L, I. And this, again, I is from 1 to T minus 1. So T minus 1 squared to T minus 1 pieces of information. And how many equations do we have? So now I'm not just considering 2, 2, 2, 2, I'm considering P, P, Q, Q. For P equals 2 to T and Q equals 2 to T. And I'm considering that at order A to the 0, and I'm considering the new supergravity result at order A.
So this is Ipson steady and company, they computed one more with respect to what was computed before.
Oh, is that all, really?
Explicitly, I think so, no? Was the 5555 do they have explicit
I
formulas?
think they have arbitrary
They
charts.
are for all of them.
I see.
Like PPQ.
But before, the one we were computing before also, up to that
They
order.
agree with the ones that
Yeah.
Oh, I see. So this PPQQ.
Yeah, right.
Ah, PQ.
I think they even have P1, P2, P3, P4, completely arbitrary.
Yeah.
So how many pieces of... So each correlator gives me an equation, it gives me the right-hand side of this equation,
Right.
these equations here. How many equations are there? Well, this is symmetric in P goes to Q. So this is T minus 1 times T divided by 2. So there's 2 of them. So it times it by 2. And that's precisely equal to that. So we have a precisely defined system of equations. Okay, so the job is to extract the right-hand sides of these equations. So, I mean, there's a bit of the story I have not mentioned yet. In that this order A piece has a part from the free theory. Sorry, I should have discussed that before. When I wrote this formula. So the free, remember I had 2, 2, 2, 2 is this free plus this plus in bracket, I say. And this is of order A. Now this bit, this is what you were referring to before, the free part, this really means free n equals 4 CPM mils. It contains 2 pieces. One is the disconnected free bit. But then it has a 1 over A times the connected bit. Okay, this was these propagators disconnected, and these were these propagators G1, 2, G2, 3, G2, 4, G4. Okay, so I need to extract the conformal partial wave coefficients of the free theory, and for that I use the first part of this talk. And then we need to also extract the partial wave expansion of the supergravity result. Well, sorry, this part has a piece from there, and it has the supergravity result.
Sorry, so you use the first part of your talk for the free.
Yes, yeah,
This
this
is
sort
the
of,
big
yeah,
coefficient.
exactly.
A bit more than that, no? I mean, aren't you, this would be trivial because this is just the disconnected, so it would be like 1 plus u over v, the one that I wrote this morning. But,
Oh, sorry, no.
but you are disentangling also the contribution of the...
Sorry, I mean, I should write this down for PPQQ. If you write everything I
No,
wrote
but
down here...
also in that case, it's just recontraction, but you are doing a bit more than that, no? Aren't you considering also how to write them in terms of...
I'm doing the conformal partial wave decomposition of those. So, yeah, they're easy to write down, but it's not so easy to extract the data from I mean, the correlators are known, but extracting the conformal partial...
block already has inside the internal part, so yes. Because you would need only one representation.
I mean, I use this SU P, P thing for P large enough, so yeah. Okay, so I obtained the right-hand side of these equations. So, namely, the right-hand side of this equation I get from the free disconnected part of PPQQ. The right-hand side of this equation I obtain partially from the free connected part and partly from the supergravity result. Very good. We, I should say. And then we have these equations. So we have t minus 1 equations for t minus 1 unknowns. And then we solve the equations essentially. So super conformal partial wave analysis gives the right-hand side of these equations, of the first two equations. solve that to find. Okay, now what are we trying to find here? So I think I did mention that before, is so to find C, P, P, C, comma L, comma I, and eta, C, comma L, comma I. Okay, so these equations here, maybe I should rewrite them in these terms. So this equation is the sum of I of C, P, P, C, comma L, comma I, C, Q, Q, C, comma L, comma I. So now I have a right-hand side of this equation, and I also have a right-hand side of this equation, which is eta I, and then multiplied by C, P, P, C, L, I, C, Q, Q, C, L, I. Okay, and from that, I can extract implies this log squared u bit. The sum from I equals 1 to g minus 1 of eta squared CPP CLI CQP CLI. So these, by the way, these etas and these c's are very nice functions. So I wrote down the c's, but the eta is it's very simple. Eta TLI is simply minus 2 t minus 1 up to t plus 2, L plus t up to L plus t plus 3, and then on the bottom, L plus 2i minus 1 up to L plus 2i plus 4. Okay, the C's are more complicated to write down, but they do have this very nice structure. Now, what do we do with that? Well, we plug these solutions into here, and this is supposed to give us the full log squared u piece. So if I label this as equation 3, full log squared u piece of 2222, the string loop correction. As an expansion in conformal blocks. But then you can sum up this expansion. And you find it has the following form. So let me write it like this: 2222 at order a squared is log squared u times a function, and the function has the following form. So it's got x1 minus x2 to the power 15 on the bottom. And on the top, it's got polynomials of degree 14, I think, in x1, x2, times polylogs of weight 2 and below. It's a big expression. Now that's not so unnatural looking, because the supergravity results we know are all d bar functions. So in the d bar functions times polylogs of weight 2 and below times polynomials. Okay, so from, so it's not completely unnatural to think of this. So, what do we do now? We have the full log squared u piece of the correlation function. What we do now is we write an ansatz down for the full correlation function.
Sorry, can I ask a question now about, so perturbatively it has a similar structure, and is it true you have computed up to many loops?
Well, be careful, there's only 3 loops for the function.
Ah, okay, 3 loops.
Many loops for the integrand, but for the
So these polylogs always have either set x1 or x2, right? They never have x1 and x2 inside.
Let me see, so with 3 loops, funny things start happening. Well, sorry, polylogs, I mean, at 3 loops.
Sorry, okay, unrelated question.
Right, so in a symbol, the symbol depends on x1,
Sorry, you're right.
x2, 1 minus x1, 1 minus x2. This appears at 3 loops. So yeah, I mean, there's certainly reason to expect more general things to appear, even just from that point of view. I mean, why? I mean, it's not something we don't know what to expect. Like this is a nice hint for what you could try. So we try 1 over x1 minus x2 to the 15 times polynomials. And the degree of the polynomial is truncated by crossing symmetry, because x1 goes to 1 over x1. So this power is why that has to be a degree of 14. Polynomials times, well, we just used polylogs at weight 4 and below. Right, we already know, we have polylogs at weight 4 here. This is the log squared u piece. Yeah. Log squared u times, at weight 2 and below.
Right, so this is for the full function.
So this is what we've computed. So this is computed, and now we're guessing the full, from here, we've guessed the full function. So now we have arbitrary coefficients over it. But we sort of impose now, of course, we impose crossing symmetry. And 2, crucially, that it matches with the log squared u result. And we get, well, first of all, we get an answer, which is nice. And there's only one free coefficient left. Okay, so, I mean, it's not particularly illuminating, unfortunately, the actual result, although, we can, it's interesting to try and simplify it. At the moment, we just put in the ansatz and saw what comes out. We have simplified it quite a bit by writing it as a 4th order differential operator on something simpler than the starting point. The nice thing would be to write it as a differential operator on phi 2 on the 2-loop box, maybe. So these guys, the d-bar functions are differential operators acting on the box functions, so it would be nice if that was the case. So we don't have that. But then from here, we can do, I mean, basically what you did in using your techniques, we can consider the log u piece. Is that my full time pad or my half time pad? Okay, but I'm getting towards the end, and don't worry, but people are like, wow, it thinks it's no, I thought it was. We can consider the log U piece of our ansatz and extract eta, how do they call it? Let me just write it delta prime, the two loop the string one loop economics dimension. So the order 1 over n to the 4th anomalous dimension. Okay, and that has a pretty nice formula. So it's given by 1, 3, 4, 4, L minus 7, L plus 14, divided by L minus 1, L plus 1 squared, L plus 6 squared, L plus 8. Well, I suppose nice depends on the point of view. And it could have been a lot worse. 2L plus 7 over L plus 1 cubed, L plus 6 cubed. Now, interestingly, let me just sort of finish with this as I can. This is for L greater than or equal to 2. Whereas for L equals 0, we get 9 over 14 alpha plus 1148 over 3.
You could call all that alpha.
Sorry?
You could have called all that alpha.
I could have called all that alpha. The reason I didn't call that alpha, this is the alpha here. The reason I didn't call it alpha is because this is what I get from that when I send L to 0. So if I assume analyticity in L, then it implies alpha equals 0. And of course as you said, alpha is just an arbitrary parameter, but we fixed it so that alpha equals 0 is the one dimension. Okay, so if we assume that, then we have this full answer within our ansatz for the string loop correction. I should also maybe add a last point is that alpha multiplies a d bar 4444, which Fernando and Agnese previously observed actually that this is a potential correction to the supergravity result. So therefore we kind of know that it has no twist 2 sector, no log squared U piece. So in actual fact, if we knew known that before, we would have known that we should see this as a correction because it satisfies all of our requirements. Because within the answer, it satisfies the requirement. Okay, good. Let me finish there.
So maybe this is a question for you guys. Is this your result?
Yeah,
As if you do an expansion of
yes,
the large L?
yes, it agrees precisely.
Oh, yeah, I should have said that. It agrees with that.
Yeah, it agrees fully.
Sorry, so your ansatz doesn't allow any making D5555, it's not in your ansatz.
No, because the reason is that you can count the powers of this thing. It's just too high, I think. Maybe 16 or 17 powers of this d bar 555.
Yeah,
it's easy to count the powers. Sorry?
It's also a solution of crossing.
Yeah, no, absolutely, yeah.
Because in principle,
Beta, D5555.
it seems that you can add in principle any crossing symmetric function.
Yes, of course. I mean, we write down this ansatz, anything that's outside our ansatz can be added. Now, of course, you guys have already analysed these particular things, and they contribute only at finite L. So unless, okay, there could be an infinite number of these corrections, in which case, we have nothing. But even if there were a finite number of such corrections, then this formula would be true for
Yeah, and it agrees also with what we find precisely.
So, Yeah, at some point you said you made an assumption about the absence of single trace and triple trace operators. Is that
Right,
connected
this is the usual kind of thing you assume in ADS-CFT, right? That the string states are supposed to develop
It's not an
infinite
assumption.
anomalous dimensions.
You can consider a regime, which is the regime of very large lambda, in which all the single trace operators in long representations acquire a very large anomalous dimension. So they don't appear in the OPE of these two protected operators. So it is a regime in which this assumption is validated.
Right. But it's kind of one of the ADS-CFT things that you have supergravity bound states, but the string states have all disappeared off to infinite anomalous dimensions.
but since all of this was doing it in expansion in 1 over lambda
Yeah.
to 1/4 or something?
Yeah.
Yes.
Well, so there are 1 over lambda corrections to this, of course.
Right.
So this is a 1 over n to the 4th corrections, but there are also 1 over lambda corrections to the supergravity result and opposed to this result.
Just to be really sure. So as n is also a set of models. So if lambda is already going to infinity,
Yeah.
we imagine the single trace will not contribute any other number r squared, but the triple trace will contribute to the next
Yeah. Yeah, so triple trace will contribute. So, what do I want to say about this? So this, I didn't specify what the anomalous dimension was. This is for a twist 4. This is for a twist 4 operator. I didn't say that. This is only for twist 4. You could imagine trying to extract twist 6 anomalous dimensions. And there, I have precisely this problem. It should mix in with a triple trace. At twist 4, there's no triple trace guy that it can mix with, so that's why we're sort of safe to extract this.
There are no other questions? Okay.